Hello there and welcome back to The Sleepless Scientist. Tonight you're standing at the edge of nothing and everything. A blank velvet black horizon stretches out before you, its silence so thick it feels like the universe has taken a breath and forgotten to exhale. Then, as if the cosmos changes its mind, the fabric of space peels open like a tired zipper, revealing a pulsing tunnel of light and distortion, sucking stars into its throat and spitting out stardust from its other end. You probably won't survive this, but hey, neither did the math that tried to explain it. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, let me know where you're tuning in from and what time it is on your little patch of Earth. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're about to learn what a wormhole actually is, and why it stubbornly refuses to behave like a portal in your favourite sci-fi show. Let's start with something simple. Imagine folding a sheet of paper in half so that two dots, one on each end, line up. That's the classic wormhole metaphor, usually pitched with smug grins by physics undergrads in dorm rooms full of ramen and unpaid rent. But reality's version is more like folding that sheet into a violent, buckling origami swan while blindfolded and on fire. You're not just connecting 2 points, you're forcing space-time itself to become your Uber driver. In its most stripped-down form, a wormhole is a hypothetical tunnel through the fabric of space and time. The term most often used is Einstein-Rosen bridge, though that name has a few issues we'll get to shortly. The idea is that if space is a three-dimensional surface, which for the moment let's pretend it is, then wormholes are shortcuts, holes that don't tunnel through space but around it, linking 2 points that might be separated by light years. And here's the magical part. You could, in theory, pop into one end of a wormhole and emerge from the other almost instantly, even if that other end is 100,000 light-years away. It's not that you travelled faster than light, it's that you cheated the course entirely. The universe set up a track, and you burrowed beneath it with a shovel and a grin. This is why wormholes are often touted as the closest thing we have to faster-than-light travel. Not because they let you break cosmic speed limits, but because they let you skip the highway altogether. But let's not get cocky. Because here's your reality check. Every known solution to Einstein's equations that allows a wormhole comes with a disclaimer the size of Jupiter. Some collapse instantly. Some require matter that may or may not exist. And some lead to places your brain isn't evolved to understand. You wanted a shortcut, and physics responded with, "At what cost though?" The earliest version of a wormhole-type solution showed up in 1916, not long after Einstein dropped his general theory of relativity like a mic. A fellow named Ludwig Flamm was poking around with equations related to black holes and noticed that they implied a sort of mirror image structure, a second universe maybe, or a way to dip between ours and another. He didn't push it far, but it was enough to plant a seed. That seed bloomed more visibly in 1935, when Einstein and his buddy Nathan Rosen cooked up a theoretical model connecting 2 black holes, hence the term Einstein-Rosen bridge. They used the geometry of Schwarzschild black holes, the simplest kind, to imagine a tunnel connecting 2 points in space-time, but spoiler, it only exists as long as no mass tries to pass through it. The instant you toss a particle in, the wormhole collapses faster than your last relationship, so technically it's there, but also completely useless. And this is where we hit our first historical moment. The Einstein-Rosen bridge was one of the earliest attempts to unify general relativity with quantum theory, at least in spirit. Einstein and Rosen weren't just trying to build portals, they were chasing a theory of everything. One that could tie electromagnetism and gravity into a neat little bow. It didn't work. But their failure became everyone else's homework assignment. Now here's a quirky side note. Some early physicists genuinely considered whether wormholes could connect not just places, but particles, as in maybe an electron and a positron are actually the two ends of a tiny wormhole. It was speculative and definitely weird, but the idea had just enough math behind it to keep it from being completely laughable. Kind of like a guy at a bar with a conspiracy theory in a spreadsheet. So what does all this mean for you, sitting here with your eyes drooping and your curiosity quietly buzzing? It means wormholes aren't portals in the Doctor Strange sense. They're brutal consequences of space bending itself into loops, knots, and tears. The kind of thing that happens when you let the universe play Jenga with your coordinates. It means that every time someone asks, "Why can't we just warp there?" the correct response is, "We're trying, Dave, but space won't stop folding in on itself like a drunk map." Historians still argue whether the early 20th century physicists truly believed wormholes could exist, or if they were just amusing themselves with high-dimensional puzzles. Some say Einstein wanted to believe. Others claim he was more interested in using them as metaphors for particle pairs. Either way, we've inherited the mathematical mess they left behind, and we're still digging through it. One last thing before we float gently forward. Wormholes, by definition, challenge everything we think we know about cause, effect, location, and even now. You might enter one in 2025 and emerge in 1732, or in a galaxy that doesn't technically exist yet. The implications are dramatic, but don't worry, we'll get to time travel headaches soon enough. For now, let's stick with the basics. You're standing before a tunnel not meant for humans, not designed by logic and not entirely stable. You don't know what's on the other side. It might be another part of your universe, or a different one entirely. And the best part? You haven't even stepped in yet. The tunnel yawns wider as you step closer, its edges wavering like heat on asphalt. You can almost hear space-time protesting, groaning under the strain of being bent, poked, and stitched into unnatural geometry. That shimmering opening in front of you, the one that shouldn't exist, has a name. Or rather, it has several. But the one that started it all is the Einstein-Rosen Bridge. And no, it's not a post-rock band from Oslo, though it probably should be. Let's rewind to 1935. Albert Einstein, who had already flipped physics on its head with his general theory of relativity, was growing increasingly irritated with quantum mechanics. He didn't like its uncertainty, its randomness, or its implication that particles could just be in two places at once like disobedient cats. Alongside his colleague Nathan Rosen, he went hunting for a theory that could unify gravity and electromagnetism, two of the four fundamental forces, and maybe clean up some of the quantum weirdness he found so distasteful. What they ended up with was a kind of bridge, purely mathematical, that linked two separate points in space-time. This wasn't a bridge you could walk across. It had no floor, no railings, no toll booths with sleepy guards. Instead, it was a connection inside a black hole solution to Einstein's field equations. Specifically, the Schwarzschild solution, which describes a non-rotating, uncharged black hole. The catch? It had a second side. A mirror image that seemed to point to an entirely separate region of the universe. The idea was elegant and infuriating. In the simplified math, the Schwarzschild black hole isn't just a singularity surrounded by an event horizon. It's got this hidden twin structure on the other side. If you string them together, they look a lot like a tunnel. A throat pinched in the middle, flaring out on either end. That's your Einstein-Rosen bridge. But don't get too excited. This bridge collapses faster than a bad soufflé. It's a mathematical ideal, a static solution that only exists in a vacuum and falls apart the moment you introduce mass, energy, or even a sneeze in its general direction. You can't send anything through it. Not a ship, not a person, not even a single photon. The minute something tries to pass through, the geometry folds in on itself, and the wormhole pinches shut like the purse strings of a miserly grandma. That's your first deal breaker, but it wouldn't be your last. Historically, the Einstein-Rosen bridge was an unexpected consequence of solving the equations of general relativity. It wasn't something Einstein and Rosen set out to find. It kind of fell out of the math like an odd sock from the dryer. And just like that sock, physicists weren't entirely sure where it came from or what to do with it. Einstein himself didn't even believe these bridges were physically real. He saw them as a mathematical trick, a way to avoid dealing with point-like singularities in particles. Still, the concept stuck. It clung to the physics community like glitter on a carpet. Not because it was useful yet, but because it teased something deeply appealing. The idea that space-time itself could be connected in ways we don't fully understand. You could, in theory, have a tunnel linking two distant regions of the universe, or two times, or two universes. Here's your required historical twist. The Einstein-Rosen bridge wasn't called a wormhole at the time. That term didn't show up until 1957, when physicists Charles Misner and John Wheeler, yes, that Wheeler, the one with the Wheeler-DeWitt equation, used it to describe these sorts of tunnel-like structures in space-time. They imagined a kind of handle in the fabric of the universe, like a shortcut poked through the geometry of a black hole. Misner even joked about them being like the holes left by worms tunneling through apples, and just like that, a metaphor was born. One that stuck hard. Quirky tidbit for you. Early theoretical wormholes were often drawn as diagrams that looked suspiciously like plumbing. Seriously, flip through the pages of some 1960s physics journals and you'll see illustrations that look like they belong in a Home Depot pipe fitting manual, which is somehow both disappointing and perfect. Now let's talk about something less quirky and more confusing. Topology. See, a wormhole isn't just a tunnel. It's a violation of the usual rules about connectedness in the universe. You're messing with the topology of space-time, its deep underlying shape. A flat sheet is one topology. A donut is another. A wormhole turns space-time into something twistier, something non-trivial. And while general relativity allows for such shapes mathematically, that doesn't mean the universe hands them out like party favours. This is where the second, grimmer reality check comes in. The Einstein-Rosen bridge is non-traversable. You can't go through it, not because it doesn't exist, but because it's structurally unstable. The moment you try to use it for anything practical, like sending a message or shoving your best friend into it, the geometry goes berserk. Space-time folds in, the throat pinches shut, and everything you were hoping to transport gets stretched into noodle form and atomized beyond recognition. So what's the point, you ask? Why spend all this energy on a structure that can't do anything? Because it opened the door. The Einstein-Rosen bridge was a foot in the cosmic crack. It inspired generations of physicists to poke harder at the equations, to ask better questions, to try to force the universe to make sense of its own shortcuts. And eventually they did start finding workarounds. Not easy ones, mind you, but loopholes in the cosmic code. Historians still argue whether Einstein wanted wormholes to be real, or whether he saw them as purely symbolic, a stand-in for a deeper connection between seemingly separate entities. Some think he was always chasing that deeper unity, a way to glue the universe together with more than just math. Others say he just wanted the quantum weirdness to go away. Either way, his bridge lives on. Not in concrete or steel, but in thought experiments, sci-fi scripts and equations that still make physicists rub their temples and mutter softly. And here's the quiet truth wormholes whisper. The universe might be connected in ways we can't yet access. The rules might bend, even if they don't break. And somewhere, behind those trembling equations and half-formed theories, there could be a path, a narrow one, a dangerous one, but a path nonetheless. You step closer to the shimmering edge, the bridge ahead might not hold, but it's there, and that's enough to keep going. You inch toward the threshold, the light around the wormhole shifting and stretching like oil on water. Every step feels slower, not because you're tired, but because space itself seems to resist you, stretching, tugging, subtly curving in ways you can't explain. This isn't normal gravity, this is math doing performance art. And now it's time to peek behind the curtain, the math of wormholes, or more accurately the math that wants to eat you alive. Let's not sugarcoat it. Wormhole physics is where equations go to stretch their legs and remind everyone that high-level general relativity is less a language and more a form of cosmic hazing. If you've ever looked at Einstein's field equations and thought, I bet I could solve that, you're either a genius, delusional, or possibly both. Because even getting the idea of a wormhole out of those equations requires a skull made of reinforced tensor calculus. At the heart of this is a deceptively simple-looking equation. Gem plus Lgem equals 8 plus G Tmn. Let's break that down gently. This won't hurt much, promise. The left side is geometry, the curvature of space-time, basically how much the fabric is bent or stretched by gravity. The right side is the energy-momentum tensor, all the stuff, mass, energy, pressure, radiation, contained within that bit of space-time. Wormholes are possible solutions to this equation, under very specific, very weird conditions. One of those conditions involves what's known as a metric, a mathematical tool that defines the shape and structure of a space-time. The most famous one for wormholes is the Morris-Thorne metric, named after physicists Michael Morris and Kip Thorne, who we'll hear more from soon. Their metric describes a traversable wormhole, which we'll get into later, but for now, know this. It looks like an innocent string of symbols and Greek letters, but hidden within is the key to building a wormhole throat that doesn't collapse faster than a reality show romance. The metric is where you'll see variables for radial coordinates, redshift functions and shape functions, terms like BR and phi-r that describe how the wormhole bends and whether light can pass through without being swallowed by an event horizon. If this sounds like a car manual written in Klingon, that's because it basically is. But math isn't just numbers here, it's the blueprint of reality. Wormholes exist as mathematical solutions before they can ever exist as physical objects. Think of it as reverse engineering a spaceship from a dream. If the equations say it's possible, maybe, just maybe, reality will agree. That said, some wormhole solutions are so exotic, they require imaginary numbers in places where real numbers should be. And no, that's not just a figure of speech. These aren't imaginary like unicorns. They're actual complex numbers, square roots of -1, showing up in space-time metrics. That's a red flag in most engineering circles, and probably a pink slip in a real lab. But in wormhole theory, it's Tuesday. Now here comes your required historical fact, and it's a beauty. The original Schwarzschild solution, the one that first suggested black holes and Einstein-Rosen bridges, was derived by Karl Schwarzschild while he was serving on the Russian front during World War I. Just imagine being in a freezing trench, surrounded by artillery fire, and casually solving one of the most important equations in modern physics on the back of a notebook. Some people write poetry under pressure. Schwarzschild redefined space. Now, despite its complexity, the math reveals something tantalizing. It suggests that under just the right conditions, a wormhole could connect not only two distant points in space, but also two different times. That's where things start to get uncomfortably spicy. We're not just warping space, we're poking holes in causality itself. There's a term you'll hear often in these equations, closed time-like curve, or CTC. It refers to a path through space-time that loops back on itself, essentially a time travel loop. If you follow it, you could return to your own past. You know, the kind of thing that keeps physicists up at night, blinking into the void and wondering if free will is just a cosmic lie. But back to wormhole math. Here's your quirky fact. In the 1980s, a few physicists tried to create simplified wormhole models using spherical symmetry and scalar fields, hoping to dodge the need for exotic matter. One of them, Matt Visser, even proposed a thin shell wormhole, a theoretical construct that sews two regions of spacetime together with a surface layer of hypothetical material. Think of it as a wormhole with a stitched-up wall made of theoretical duct tape. Charming. Of course, you'll never see these equations written out on a cafe napkin. They usually show up in intimidating papers full of dense notation and enough subscripts to make a typewriter explode. But tucked inside those symbols is the thing that makes wormholes so compelling. They're not magic, they're math. Very weird, very demanding math, but math nonetheless. And math is something the universe tends to take seriously. Historians still argue whether the emphasis on math-first wormhole models has distracted us from practical approaches. Some believe the theory has spiraled too far into abstraction, chasing elegance over applicability. Others argue that without the math, we'd have no roadmap at all. No one's suggesting you'll build a wormhole in your garage unless your garage contains a particle accelerator and a budget that rivals NASA's, but understanding them begins with the numbers. Now, if you're feeling like your brain just tried to fold in on itself, you're not alone. Wormhole physics sits at the junction of geometry, quantum theory, and sheer stubborn optimism. It's like trying to win a game of chess where the rules change every 3 moves, and sometimes the bishop is a black hole. Still, the math tells a story. A warped, beautiful, borderline incomprehensible story about the universe not being flat and fixed, but twisty and full of loopholes. And if the numbers are right, and the signs continue to point to maybe, then a shortcut across light years might not be pure fantasy. But we're not ready to travel yet. You're still standing outside the wormhole, listening to space-time hiss and stretch. The equations swirl around you, invisible but undeniable. Somewhere deep inside them, a possibility is whispering, one that says, if the math fits, step through. The tunnel flickers again, and this time the shimmer isn't just optical, it's mathematical. Space doesn't behave like this unless something very strange is holding it together. Something that isn't behaving according to any of the polite, predictable rules of normal matter. And that brings us to the real question now. If most wormholes collapse instantly, what would it take to keep one open? 2 words, traversable wormhole, and if that sounds a bit like a glorified hiking trail in the Grand Canyon, don't worry. We're still talking about cosmic plumbing, but now you're allowed to walk through it. Enter Kip Thorne. Yes, the same Kip Thorne who advised Interstellar and made sure that the black hole in that movie didn't look like a cartoon toilet. Back in the 1980s, Thorne and his grad student Michael Morris decided to tackle a problem most physicists were too cautious or too realistic to touch. What would it actually take to make a wormhole that you could travel through without dying horribly? Spoiler, it wasn't easy. Most solutions to the Einstein field equations, like the Einstein-Rosen bridge, produced wormholes that were non-traversable, throats that snapped shut before you could even say quantum instability. But Thorne and Morris decided to flip the problem on its head. Instead of finding a natural wormhole and trying to survive it, they started by designing one that would let a human pass through safely, then reverse engineered the conditions needed to keep it open. And that's when things got weird. To keep the throat of a wormhole from collapsing under the crushing force of gravity, you'd need something to counteract that force. Not normal matter, not even neutron star level matter. You'd need exotic matter, a form of energy or mass that generates negative pressure. In other words, it would need to push space-time outward instead of pulling it inward like everything else does. And here's your obligatory historical anchor. This was the first time a scientific paper proposed wormholes as a serious tool for time travel and faster-than-light travel, not as a side effect, but as a goal. The 1988 paper by Morris and Thorne laid out the conditions clearly. You'd need a throat wide enough to travel through, with tidal forces low enough that a person wouldn't be shredded into spaghetti. And to support it, you'd need something that violates the null energy condition. Let's take a slow breath through that one. The null energy condition is one of the many assumed laws of classical physics, and it says, in very simplified terms, that energy density along any light-like path must be non-negative. Translation: light travelling through the universe shouldn't suddenly gain or lose energy just by existing. But exotic matter doesn't care. It laughs in the face of the null energy condition. It creates situations where gravity repels instead of attracts, where space pushes instead of squeezes. And if you pack enough of it into the right configuration, you can, on paper, prop open the mouth of a wormhole and keep it from collapsing into a singularity. And now for your fringe tidbit. Some researchers have speculated that dark energy, the mysterious force accelerating the expansion of the universe, might be related to exotic matter. It's not a mainstream idea, but it's just plausible enough to make theoretical physicists squint at their chalkboards and wonder if the universe is already sprinkled with the ingredients for wormhole construction. So here's how your traversable wormhole might look. You've got two mouths separated by vast distances. The tunnel connecting them is called the throat, and it needs to be wide enough to fit a spaceship, a person, or at the very least, a stylish cosmic road trip van. The interior geometry has to be carefully shaped to avoid tidal forces that would squash travellers like bugs under a textbook. The whole structure has to be supported by negative energy density material placed in just the right configuration to keep the throat open indefinitely. It's not easy. It's like trying to inflate a balloon made of gelatin, using a pump that runs on antimatter, while standing in a hurricane made of equations. Historians still argue whether Morris and Thorne's work actually made wormholes more plausible, or just made the fantasy sound fancier. Some critics pointed out that exotic matter might not even exist, while others complained that if it did, producing enough of it to prop open a wormhole would require more energy than exists in the visible universe. Still, others saw it as a necessary step, proof that general relativity wasn't the one standing in the way. It was just everything else. The paper became instantly famous, both inside and outside the scientific community. Carl Sagan even reached out to Thorne while writing Contact, asking how a scientifically plausible wormhole might work for his story. Thorne obliged, and the result was the first popular depiction of a wormhole grounded in actual physics, albeit with generous creative license. Here's the quiet tragedy. No one has ever seen a wormhole, not even a closed one, not even a tiny flicker of one. There are no astrophysical signatures, no shadows on the cosmic microwave background, no unexpected gravitational lensing effects. Yet, if they exist, they're hiding very, very well, or they're so small we'd never notice. Still, we now have a theoretical framework, a blueprint, however unstable. We know what the rules are, we know what kind of materials we'd need, we even know what kinds of observations might reveal them. So as you stare into the gently humming throat of this hypothetical wormhole, know that someone out there, probably sitting in a windowless lab with 17 cups of coffee and a blackboard full of Greek letters, is still trying to make this thing real. And here's the last twist. The traversable wormhole solution implies a paradox. If you could build one, and then drag one mouth at near-light speeds away from the other, you'd create a time shift between the mouths. Enter one, and you might exit before you left. Time travel, baked into the recipe. More on that soon. For now, just let the thought simmer. The tunnel remains open, for now. But it's only possible because of matter that shouldn't exist, in a universe that probably doesn't hand out shortcuts for free. Still, you have to admit, it's beautiful. You move closer, and the air itself seems to hush, like the cosmos is holding its breath. There's a faint vibration now, Not sound exactly, but something deeper, more primal. A hum beneath existence, pulsing through the tunnel's frame. You sense, without quite understanding, that this is not an empty hole. Something is keeping it open. Something unnatural. Something exotic. Yes, it's time to meet the star of our cosmic freak show, exotic matter, physics-moody, rule-breaking, reality-defying troublemaker. Let's get something straight. Exotic matter isn't just strange, it's unthinkably strange. It violates the most basic principles you've come to trust, like gravity pulling inward or energy having a positive value. Exotic matter stares down Newton and Einstein, yawns, and does a little pirouette of negative energy density. Negative energy. Let those words sit for a moment. Not just an absence of energy, less than nothing, as if the universe owes it a favour. And if that sounds like a concept stolen from a bad sci-fi paperback, well, it is. But it's also real in the theoretical sense. That's the weird magic of physics. What seems impossible can still be mathematically required. To understand why you need exotic matter for a traversable wormhole, think of the tunnel as fighting an uphill battle against the natural tendency of space-time to collapse. Gravity wants to crush the wormhole throat. It hates the idea of a stable shortcut. To counteract that, you need something with the opposite effect. Something that repels instead of attracts. That's where exotic matter comes in. Here's a strange but true moment from modern science. We've actually observed negative energy in the lab. It's called the Casimir effect, and it's not just a theoretical toy, it's a measurable phenomenon. When you place two uncharged parallel metal plates very close together in a vacuum, they experience a tiny force pulling them together. That force exists because quantum fluctuations are suppressed between the plates, creating a region of lower than normal energy. In other words, a negative energy density. Real, measured, exotic. But before you start stacking aluminum sheets together hoping to build your own wormhole in the garage, take a breath. The Casimir effect is teeny tiny. The amount of negative energy involved is so small, you'd need the energy output of a small star just to scale it up into something usable. And even then, we have no idea how to make it stay put or maintain stability inside a wormhole throat. Now, exotic matter doesn't just break the null energy condition, which we mentioned last time, it also breaks the weak energy condition, the strong energy condition, and occasionally your spirit. These conditions are the cosmic equivalents of saying mass and energy should behave politely, and exotic matter just flips every table it sees. Quirky fact time. Some early theoretical models suggested that faster-than-light particles, called tachyons, might be a form of exotic matter. These hypothetical particles would always move faster than light and have imaginary mass. Yes, imaginary as in square root of -1 again. We've never seen a tachyon, and if they exist, they're hiding better than your missing socks. But the idea of exotic matter always seems to pull in the fringe, the speculative, the beautifully ridiculous. Historians still argue whether exotic matter is truly a feature of the universe or just a mathematical kludge, a placeholder for something we haven't figured out yet. Some believe that it might only appear in certain extreme quantum gravity scenarios, like near black hole event horizons or in high-energy string theory landscapes. Others think exotic matter is a polite way of saying, our equations got weird and we don't know why. But here's where things get really interesting. If exotic matter can exist at scale, it doesn't just open up wormholes. It could redefine what's possible in physics. Think warp drives, Alcubierre's warp bubble, the theoretical concept for stretching space behind a spacecraft while contracting it in front, also requires negative energy. Think time machines. Stable wormholes with exotic matter could allow closed time-like curves. Think cosmic engineering on a scale we can barely imagine. And now we take a brief moment to panic. Because if we could eventually create exotic matter, what if someone else already has? What if there are civilizations out there who've harnessed it to build wormhole networks, warp drives, or even planetary-scale quantum computers powered by reality-bending materials? It's the kind of idea that keeps SETI researchers awake at night and conspiracy theorists scribbling furiously on corkboards. We'll come back to aliens later. Don't worry, that rabbit hole is coming. For now, just know this. Exotic matter is the key to everything wormhole related. Without it, every tunnel collapses. With it, you unlock the closest thing the universe offers to cheating. But there's a catch. Of course there is. Even if we could manufacture exotic matter, we'd need obscene amounts of it to keep a wormhole open long enough to be useful. We're not talking kilograms. We're talking energy masses equivalent to Jupiter, carefully distributed, stabilized, and kept from leaking or collapsing. And that's assuming we can even control this stuff. Exotic matter, by definition, might behave in ways that defy every engineering principle we know. You might store it in a chamber, only for the chamber to warp into a pretzel and vanish into an alternate dimension. You might power it up, only for causality to unravel and your coffee to age backwards. This is the cosmic price tag. The universe doesn't offer shortcuts for free. It demands strange ingredients, impossible conditions, and the willingness to play chicken with the laws of reality. Still, even the idea that exotic matter might exist is enough to keep wormhole physicists working late. It's the linchpin, the hope, the one card that might make the whole deck work. And while we don't know how to produce it, confine it, or control it, the equations whisper that it's there, lurking in the quantum foam, flickering at the edge of known physics, just waiting to be summoned. And as you step even closer to that theoretical wormhole, you realize something profound. It's not just the geometry holding it together. It's this elusive, impossible substance. The kind of thing that shouldn't be real, and yet might be more real than we've dared to believe. The tunnel flickers again, and now you're close enough to feel its pull, not just gravitational, but intellectual. It's daring you to step through, to gamble on negative energy, to bet on the unknown. You haven't stepped in yet, but you're beginning to believe. The closer you get to the wormhole, the more the edges of reality feel like they're made of jelly. The stars behind you blur just a little too fast when you glance back, and for a moment, you're not sure if your foot is on solid ground, or if space just forgot to render the floor properly. And that's when it hits you. Maybe wormholes aren't rare at all. Maybe they're everywhere, just small, fast, and completely unstable. Maybe they live in the fabric of the universe itself, flickering in and out like cosmic static. Welcome to the chaotic world of quantum foam. Now, if quantum foam sounds like something you'd spray on your driveway to remove oil stains, you're not alone. The name is squishy and weird, and to be fair, so is the concept. But this isn't just some theoretical garnish on top of quantum mechanics. It's one of the strangest, most fascinating ideas to emerge from the crossroads of quantum theory and general relativity. Let's start at the beginning. Imagine zooming in on empty space. You pass atoms, electrons, protons. You pass the scale of quarks, then gluons, then deeper still, way past the reach of any microscope or particle collider. Eventually you hit the Planck scale, a mind-bogglingly tiny distance of about 10 to the negative 35th meters. That's where space-time stops being smooth and becomes a seething, jittering mess of energy fluctuations, particle-antiparticle pairs popping in and out of existence, and space itself bubbling like boiling water. This is quantum foam. Coined by John Wheeler, the same physicist who helped popularize the term wormhole, it describes a picture of the universe that, at its smallest scale, isn't calm or orderly at all. Instead, it's a quantum storm, a frothing chaos of microscopic space-time warps, flickers, and fluctuations. And here's the kicker. Some physicists believe that wormholes might spontaneously form and vanish inside this foam, tiny, temporary tunnels appearing between different regions of space-time. We're not talking human-sized wormholes. These are unimaginably small, on the order of the Planck length, but in theory they're real. They're called virtual wormholes, and they might be forming around you right now, constantly, like invisible gnats in the air. They live for a fraction of a second, mere whispers in the quantum void, and just like virtual particles, they're allowed to exist briefly, as long as they vanish fast enough to obey the Heisenberg uncertainty principle. In other words, the universe lets them cheat, but only if they disappear before anyone notices. It's the ultimate game of subatomic hide-and-seek. Here's a quirky fact to make this even weirder. Some theoretical physicists in the 1990s suggested that information, yes, actual data, might be able to pass through these microscopic wormholes, providing a kind of quantum-level communication channel across space. It's extremely speculative and has little empirical backing, but it remains one of the more deliciously strange side dishes in the buffet of quantum gravity research. Now, you may be wondering, if these tiny wormholes are real, could they ever grow big enough to use? That's one of the billion-dollar questions. Some have proposed that, if you could somehow find one of these virtual wormholes and stabilize it with exotic matter, like stretching a soap bubble without popping it, you might be able to scale it up. That means taking a microscopic transient feature of quantum foam and inflating it into a full-blown traversable wormhole. It's like trying to build a tunnel by catching a lightning bolt and convincing it to stay still. It would require enormous precision, obscene energy, and the ability to manipulate the fabric of space-time at quantum scales. So, trivial stuff. Still, even if we never manage to upscale a wormhole, the very existence of quantum foam has implications that ripple through the rest of theoretical physics. For one, it's central to any attempt to develop a theory of quantum gravity, a unified framework that merges general relativity, our best theory of gravity, with quantum mechanics, our best theory of the very small. These two theories normally don't get along. They operate like divorced parents trying to co-parent a hyperactive child called reality. Quantum foam is where they both show up and argue the loudest. Historians still argue whether the concept of quantum foam is a placeholder, a metaphor we use to describe our ignorance, or a genuine feature of space-time that will one day be confirmed. Some argue it's inevitable, the natural consequence of applying quantum uncertainty to gravitational fields. Others suggest that future theories like loop quantum gravity or string theory may describe the Planck scale world differently, and quantum foam could turn out to be an illusion. But even if it's an illusion, it's a useful one, and one that just might explain one of the most persistent puzzles in all of physics: why gravity is so weak compared to the other forces. Some speculative theories propose that gravity leaks into tiny hidden dimensions curled up inside the foam. Others argue that wormhole-like connections between distant parts of the universe might dilute gravitational strength, basically cosmic cheating via quantum networking. And now, here's a little-known fringe idea to sprinkle on top. Some physicists have wondered whether quantum entanglement might be connected to tiny wormholes. If that sounds suspiciously familiar, you're right. It leads us straight into the ER equals EPR conjecture, but that's still a few steps ahead. For now, you're left standing at the edge of a wormhole, thinking not just about the massive cinematic portals seen in movies, but about the endless ocean of microscopic ones potentially blinking in and out of existence all around you. They're not useful, not yet. They don't last long enough to walk through, but their very existence suggests that space-time isn't solid and smooth, but twitchy and twitching, always on the verge of sprouting a hole, a loop, a shortcut. And that's the unsettling beauty of it. Wormholes might not be engineered. They might be natural, even common, just hiding at a scale we can't yet reach. You watch the tunnel flicker again, and for a moment the surface of the wormhole throat resembles foam. Rippling, turbulent, full of possibility. It might not be real, but it might be a preview of the deeper chaos waiting inside every particle of the universe. The path ahead is no longer just theoretical, it's starting to feel inevitable. You take one cautious step closer. The tunnel no longer looks like a gentle ripple in space, it looks alive, pulsing, stretching, breathing in some slow, incomprehensible rhythm. A black ring frames the entrance, and beyond it lies nothing you can quite describe. Light bends in sickening curves, and for a moment you think you see the stars behind you through the tunnel's far end, but upside down and slightly older. This isn't just a wormhole anymore, it's starting to look a lot like a black hole, and that makes sense because wormholes and black holes are close relatives, like distant cousins who were once the same zygote, then chose wildly different life paths. One became a terrifying gravity well that eats everything. The other is a hypothetical cosmic shortcut that barely stays alive unless it's constantly babysat by exotic matter and theoretical physicists. Let's be clear, not all black holes are wormholes, and not all wormholes are black holes, but the family resemblance is undeniable. It starts with the Schwarzschild solution, the same Einstein field equation solution we keep bumping into. It describes a non-rotating, uncharged black hole. No bells, no whistles, and when you dig into its mathematical guts, it contains something that looks suspiciously like a wormhole, the Einstein-Rosen bridge. But as you might recall, that bridge collapses instantly, and it's only traversable if you're light, and only if you're willing to never come back. So what happens if you actually fall into a real black hole? Say goodbye to casual physics and hello to event horizons, gravitational time dilation, and the rather unpleasant concept of spaghettification. That's right, because the closer you get to the singularity, the more stretched you become. Your feet feel stronger gravity than your head. That differential force, while you're accelerating at a sickening rate, pulls you into a long, thin noodle of atoms. It's not elegant, it's just painful and final. Here's your historical tidbit. John Archibald Wheeler coined the term black hole in 1967, despite the concept having been around for decades under much less snappy names like frozen star or gravitationally completely collapsed object. Marketing really is everything. Black holes, unlike wormholes, definitely exist. We've photographed their shadows, we've measured their effects on nearby stars, we've even heard them, well, their gravitational wave echoes, thanks to LIGO-detecting black hole mergers. They're real, they're massive, and they're terrifying. And yet some physicists still quietly hope that inside or near, or just beyond a black hole's event horizon, there might be a hidden wormhole, a tunnel, a portal, a back door through space-time, and it's not impossible. Certain rotating black hole solutions, like the Kerr metric, allow for strange internal structures. The math gets twisty and brutal, but under very specific conditions, it appears that a spinning black hole might contain a ring singularity, a place where space-time curves, yes, but doesn't collapse to a point. And tucked inside that chaotic geometry, you get something that looks like a pathway. Some models even suggest that entering a Kerr black hole from the right trajectory might allow you to avoid the singularity entirely and pass through to another region of space-time. But before you start planning a vacation, here's the fine print. Any tiny perturbation, like a speck of dust or a single photon, would destabilize the whole thing and slam the tunnel shut. No warning, no refunds. Quirky theory break. There's a fringe idea that certain primordial black holes, tiny black holes that might have formed right after the Big Bang, could still exist, and some of them might be wormholes. Tiny, ancient, lurking in the dark matter haze of the galaxy, not swallowing stars but hiding. quietly warping space-time without making a fuss. If real, they'd be the best cosmic prank in history. And yes, we've tried to look for them. So far, nada. But keep your eyes on the weird lensing patterns of distant galaxies. One day, we might catch one wobbling. Historians still argue whether the connection between black holes and wormholes is a physical reality or just a mathematical artifact. Some physicists argue that wormholes are purely a result of idealized symmetrical conditions that never actually occur in nature. Others believe that under certain quantum gravity theories, black holes could transition into wormholes if the right exotic conditions are met at the core. Let's also not forget the big problem with black holes, the singularity. It's the end of known physics. General relativity breaks down. Quantum mechanics shrugs. The math explodes into infinity. And right at that spot, at the center of a black hole, is where some physicists have suggested that a wormhole might form as a pressure release valve, so to speak. There's also the hopeful speculation that black holes might not end in destruction, but in white holes, the theoretical inverse of a black hole, which emits matter instead of consuming it. Sounds insane? Absolutely. But the math allows it, and in certain bouncing cosmologies and loop quantum gravity models, black holes eventually turn into white holes via quantum tunneling, essentially spitting out everything they've ever eaten across time. It's gross, and maybe kind of beautiful. If that's true, if a black hole eventually turns into a white hole, it would technically be a one-way wormhole, a cosmic meat grinder with an exit hatch. Not a portal you'd want to use voluntarily, but still a shortcut of sorts. The line between black holes and wormholes isn't just fuzzy, it's quantum fuzzy. The two might be twins, or at least deeply connected under some as yet unknown theory that binds gravity and quantum physics into a single unified fabric. So now, standing at the edge of this theoretical wormhole, you wonder, is this really a shortcut through space and time? Or is it just a very patient black hole, waiting for you to come a little closer? Because here's the uncomfortable truth. From a distance, you can't tell the difference. A traversable wormhole could look exactly like a black hole until you're already falling in. Same gravitational lensing, same event horizon, if it even has one. You might not know until it's too late, and that ambiguity is why so many physicists remain cautious. Because we know black holes are real, and they do not let you leave. Still, the hope remains that somewhere out there, maybe even inside the gravitational chaos of a black hole, there lies a stable tunnel, a mouth, a path, and that's what keeps researchers up at night, and maybe makes you hesitate just for a second before taking that last step into the throat. The pull is growing stronger, you're not falling, not yet. But something is calling you forward. The mouth of the wormhole looms larger now, humming in a pitch your ears can't quite catch, but your bones absolutely can. It's like standing near a power station built by alien hands, every vibration whispering secrets your nervous system pretends not to understand. You haven't stepped inside, not yet, but already time feels strange, thick maybe, loose, and you should know, if you're going to dance with wormholes, you're also going to be flirting dangerously close with closed time-like curves. You may not want to know what that means, but you will. Let's break it gently. A closed time-like curve, or CTC, is a path through space-time that loops back on itself. Imagine walking in a straight line only to find yourself right back where you started, but not just in space, in time. And wormholes, under certain conditions, don't just allow this, they basically dare you to try. Here's how it works in theory. You take one mouth of a wormhole and accelerate it near the speed of light, say, on a long trip around the galaxy. Thanks to special relativity, time for the moving wormhole mouth slows down compared to the one that stayed at home. So when you bring the two mouths back together, they're now desynchronized. One is in the present, the other is in the past relative to it. Now, if you step into the older mouth, you'll exit the younger one, and boom, you've travelled backward in time. You didn't break the speed of light, you didn't cheat the laws of physics, you just bent the map. And yes, your headache is completely valid. Historically speaking, this idea really caught fire in the late 1980s and early 90s, especially thanks to Kip Thorne and his collaborators. Their theoretical models showed that a traversable wormhole, if one could be built and manipulated, wouldn't just allow interstellar travel. It would allow time travel in the most literal, awkward sense. The universe apparently has a soft spot for paradoxes, and those paradoxes? Oh, they're juicy! The moment you introduce closed time-like curves, you get causality violations. That's a fancy way of saying, what happens if you prevent yourself from going back in time after you've already done it? Cue the grandfather paradox. You know the one. Go back in time accidentally, or not so accidentally. Remove your grandfather from the timeline, and poof, you were never born to time travel in the first place, which means you never went back, which means time uncollapses, or doubles back, or just stands awkwardly in a corner with a drink. Here's a fringe twist. Some physicists argue that paradoxes don't actually prevent time travel. They just enforce consistency. That's the essence of the Novikov self-consistency principle, which says that if a timeline includes time travel, then events must be self-consistent. You can go back in time, sure, but whatever you do was already baked into the timeline. You're not changing the past, you're fulfilling it. It's fate, dressed up as physics. So in that scenario, you might go back and try to change something, but every attempt fails or inadvertently causes the very thing you wanted to prevent. It's not free will, it's closed-circuit destiny. And yes, it's incredibly annoying if you're the type who likes to control outcomes. Here's a historical flavour boost. Kurt Gödel, yes, the incompleteness theorem guy, was one of the first to propose a rotating universe solution that allowed for closed time-like curves. In 1949, just casually doing some cosmic math, he realised that a spinning universe could permit paths that curve back in time. It was elegant, deeply disturbing, and, fortunately or unfortunately, almost certainly not our actual universe. And now for your quirky fact of the night. There was a period in the early 2000s where physicists seriously considered using wormholes not just for time travel, but for communication across time. Send a message from the future to the past using a carefully controlled wormhole with desynchronized mouths. No paradox, just delayed delivery with a timeline twist. Imagine the cosmic email chain. Don't invest in NFTs. Sincerely, 2028. But back to the present, or whatever we're calling this now. There's a big glaring issue with all of this. Wormholes that allow time travel also open the door to feedback loops, closed causal cycles where events cause themselves. For example, you receive a blueprint from the future, build the wormhole, and then send the blueprint back in time. No one actually invents anything. It's just a blueprint that loops endlessly through time, without origin. These are called bootstrap paradoxes, and they're as fascinating as they are unsettling. They suggest a universe where some things exist not because they were created, but because they're stuck in a loop of causality. Information, objects, maybe even people, just circulating endlessly, untethered from any starting point. Historians and physicists still argue whether this is physically plausible or just philosophical funhouse logic. Some believe closed time-like curves break the rules so badly that the universe would find a way to destroy the wormhole before it allowed any such nonsense. But others aren't so sure. In fact, some quantum physicists think that time travel via wormholes might be allowed, but heavily regulated by probability. That is, the universe permits closed loops, but only ones with a high enough chance of occurring without contradictions. You could go back in time, sure, but only if the path you take doesn't shatter the consistency of the quantum wave function. That's right, Quantum mechanics might have the final say on time travel, and speaking of which, don't get too comfortable. Time travel through wormholes doesn't come with insurance. Stabilizing the wormhole to keep the timeshift stable would require maintaining exact geometrical conditions, keeping the exotic matter in just the right configuration, and avoiding any disturbance that could collapse the whole structure like a flan in a thunderstorm. And even if you could do it, there's another horrifying possibility. Time travel through a wormhole could create runaway feedback in the form of radiation. Physicist William Hiscock pointed out that quantum fluctuations, tiny energy jitters in space-time, could spiral through a wormhole with a time difference and amplify themselves infinitely, creating a kind of radiation death spiral that destroys the wormhole the moment a time loop becomes possible. It's like the universe sees what you're doing and says, okay, that's enough of that, before unleashing a gamma-ray slap. Still, the idea lingers. Wormholes don't just promise space travel, they whisper of time travel. They hold the potential to curve not just where you are, but when. You haven't stepped in yet, but you're feeling it now. That gentle tug at the corners of your memory. The sense that maybe this already happened. Maybe you already walked through, and this is you, remembering the first time. Or the last. Time, it turns out, is not a polite house guest. The moment you invite it to loop, tangle, or fold through a wormhole, it starts rearranging the furniture of physics and knocking over every fragile theory in its way. And the universe? It might not appreciate that, because just when it seems like time travel via wormholes might be theoretically possible, even if absurdly difficult, along comes Stephen Hawking with a clipboard, a pen, and a raised eyebrow. He's not angry, just disappointed. And he proposes something with the kind of elegance and finality that only a genius with a cheeky grin could deliver. It's called the chronology protection conjecture. Hawking's big idea, first suggested in 1992, is this. The laws of physics themselves might prevent time travel automatically before it ever happens. No need for cosmic police or multiverse bouncers, just built-in safety mechanisms buried in the mathematics of space-time, like a parental lock on the fabric of reality. In other words, if you try to use a wormhole to create a closed time-like curve, go back and high-five your past self, stop a disaster, or just see what you looked like with 2006 hair, the universe might respond with a polite but firm nope, and then obliterate the wormhole with a quantum tantrum. How? With feedback loops. Remember that thing from earlier? The idea that radiation passing through a wormhole could bounce back and forth if the mouths are time-shifted? Yeah, that's the one. Each pass adds more energy, building up in a crescendo until the wormhole collapses under its own amplified quantum noise. It's like shouting into a microphone while holding it next to a speaker, except your entire shortcut through time explodes. This feedback is called vacuum polarization, and it's a quantum effect that gets cranky when space and time start acting funny. As the wormhole approaches the threshold of forming a closed time-like curve, the energy from virtual particles bouncing through the loop grows rapidly, potentially infinitely, until the structure destabilizes. It's not just theoretical, it's plausible. And that's why Hawking proposed that any scenario allowing for time travel via wormholes would destroy itself before the loop could be completed. It's not that the universe hates time travel, it's just very, very allergic to paradoxes. Here's your historical moment. Hawking's chronology protection conjecture wasn't proven, but it has never been refuted either. Many physicists take it seriously not because it's airtight, but because it elegantly solves a problem that every other approach keeps tripping over. It suggests that while wormholes might allow FTL-like travel, they probably won't let you visit your own past. At best, you could exit at a point in the future, or in a different part of the universe, but the moment a time loop is possible, boom, self-destruction. And yet, despite this doom and gloom, not everyone agrees. Some physicists still argue that the universe might allow time travel under highly restricted circumstances, or that quantum gravity, our long-lost theory of everything, might eventually reveal safe pathways through the causal minefield. Others have suggested that certain exotic conditions like post-selected quantum states might avoid paradoxes entirely, allowing for time travel that self-corrects. There's also the idea of the many worlds interpretation. In this scenario, when you travel back in time, you don't overwrite your own timeline, you jump to a parallel one. No paradox. Just an awkward copy of yourself who now has to explain why you're wearing 2 watches and seem unreasonably informed about future sports scores. It's an elegant dodge. But Hawking's conjecture still looms. His core idea is simple. Even if time travel is allowed by the math, the physical processes of the universe might automatically shut it down. Quirky side note: Hawking once hosted a party for time travelers. He printed invitations and sent them out after the event happened, reasoning that if anyone did show up, they'd clearly have access to time travel. No one came, which, according to Hawking, was the most convincing experimental evidence against time travel I've ever seen. It's charming and kind of tragic, because the dream of time travel is ancient, woven into myths, stories, and now equations. Wormholes gave it a glimmer of hope, a route, a loophole, and the universe, being the ultimate party pooper, might just slam the door shut every time we get close. Still, the debate rages on. Historians and physicists argue whether chronology protection is an unbreakable rule or a strong suggestion. Some think there's wiggle room, that nature is more flexible than Hawking gave it credit for. Others believe it's not a law, it's a mercy. Because let's be honest, the ability to travel through time raises uncomfortable questions: free will, determinism, identity. If you can change the past, who are you now? If you can see the future, does it already exist? And perhaps most unnervingly, if wormholes can be used to travel back in time, where are all the time travelers? That's the Fermi paradox's slightly weirder cousin. If wormholes exist and time travel is possible, why aren't we being visited constantly? Why no messages from the future? No glimpse of future tech? No mysterious strangers in lab coats handing out antimatter batteries? Maybe time travel is too dangerous. Maybe it's only possible after a certain moment in history, say, after a wormhole is first constructed. Maybe the first wormhole mouth marks a fixed point. You can go forward from it or back to it, but never before it. That's one of the more optimistic interpretations. Or maybe Hawking was right. Maybe the universe protects itself. So now, standing at the wormhole's edge, you realise something uncomfortable. Stepping through might not just bend space, it might bend time, and that could trigger a self-destruct. You take a breath. The tunnel seems stable, for now, but you swear it's listening. Because if time itself can be broken, the universe seems determined to make sure it never is. You pause just a breath away from the edge of the tunnel and stare into the gaping throat of space-time. It's quiet now, deceptively calm, like the moment in a horror movie right before the hallway screams. You've waded through the math, toyed with the timelines, flirted with paradoxes, and somehow you're still standing. But let's take a step sideways. While science slowly works through its existential wormhole crisis, pop culture has already decided what wormholes look like, how they work, and which actor is allowed to dramatically fly through one in a sleek spaceship, accompanied by a swell of orchestral music. Welcome to the land of wormholes in pop culture, so wrong it hurts. And let's be honest, this is where most of us first met wormholes, not in dusty physics journals, but in dark movie theatres, in the pages of sci-fi novels, or while watching late-night reruns of Star Trek episodes with budget constraints and questionable hairpieces. Let's start with one of the all-time big ones, Interstellar. Yes, the 2014 Christopher Nolan epic, where astronauts pass through a wormhole conveniently parked near Saturn and end up orbiting a black hole named Gargantua. What Interstellar gets right, thanks in large part to Kip Thorne's consulting, is the basic visual and gravitational effects. The wormhole is shown as a sphere, not a hole in space, which is accurate. The depiction of time dilation near the black hole is also surprisingly well done. You may recall the scene where 1 hour on the planet near Gargantua equals 7 years elsewhere. That's not movie magic, that's general relativity, and it's horrifyingly real. But even in this science-boosted film we get a few stretches. The wormhole is stable, conveniently traversable, and somehow just sitting there in space, like an interstellar bus stop. There's a vague reference to them, an advanced future civilization, or maybe humans themselves, that supposedly placed the wormhole near Earth. And sure, that solves the origin problem in the most hand-wavy way possible. But also, come on. Then there's the moment where Matthew McConaughey drops into the black hole and ends up in a fifth-dimensional bookshelf where he sends gravitational Morse code to his daughter across time. Beautiful? Yes. Scientifically airtight. Let's just say Kip Thorne made a few allowances for narrative drama. Still, Interstellar remains one of the best depictions of wormholes in cinema, if only because it tried to stay loyal to the physics, at least until Act 3 gave way to feelings and the power of love. Now contrast that with Stargate. In this cult favourite series, wormholes are opened using giant rings powered by alien tech and activated via chevrons and address codes. The rules change from episode to episode. Sometimes you can only stay in one for 38 minutes. Sometimes you can dial anywhere in the galaxy. And sometimes the wormhole just decides to implode a planet because the writers were late on a deadline. Is it fun? Yes. Is it science? Not even slightly. Then there's Doctor Who, where time travel is less wormhole and more narrative fever dream, complete with spinning police boxes and paradoxes you're not supposed to think too hard about, and we won't. Of course, no pop culture wormhole tour is complete without Rick and Morty, where portals open with the click of a green gun and lead to infinite realities, including one where everything is just corn. It's chaos, it's satire, and it's actually sneakily insightful. The show regularly riffs on the idea of quantum multiverses and infinite timelines, though it doesn't bother much with the structural stability of the wormholes it creates. And let's not forget Event Horizon, the 1997 horror film that claimed wormholes could punch through to another dimension, which turns out to be literal hell. You won't find that in a peer-reviewed journal, but it gets points for creativity and trauma. Here's a fun, little-known fact. Carl Sagan's novel Contact originally featured conventional space travel, but after consulting Kip Thorne, Sagan rewrote the script to include wormholes as the preferred method of FTL travel. That's how deeply science influenced that story, and how carefully it tried to stay within the boundaries of what physics might allow. The film version even uses some of the same logic we've discussed, a shortcut through space-time that doesn't technically violate relativity. Historians still argue whether popular depictions of wormholes help or harm public understanding of science. On one hand, they inspire interest, spark imagination, and introduce real scientific concepts to audiences who'd never read a physics paper in their lives. On the other hand, they often flatten or distort the truth so badly that people walk away thinking wormholes are just space doorways you can jump through like a video game. And look, we get it. Actual wormhole physics is complicated, slow, and full of exotic matter and potentially fatal side effects. You can't fit that into a tight 90-minute plot without losing some of the thrill, but still, some shows try harder than others. Take The Expanse, for example. While not dealing with wormholes directly, it gives us the Ring Network, a series of portals created by ancient alien tech that obey semi-consistent rules about velocity, energy, and conservation. It doesn't pretend to be natural, it's clearly a construct. And yet it still manages to feel grounded, like a believable piece of future technology with terrifying consequences when misused. And then there's Tenet. Does it use wormholes? Not exactly. but its backward time travel mechanics flirt with closed time-like curves and temporal inversion in ways that would make Hawking sigh deeply and reach for a glass of wine. So where does that leave you standing at the edge of your own wormhole? Pop culture has filled your head with glowing tunnels, spinning lights, and soundtracks swelling just as the portal stabilizes. Reality, meanwhile, offers equations, uncertainty, exotic matter, and vacuum polarization. But here's the thing. Pop culture isn't completely wrong. It's just early. It's the preview trailer before the full science arrives. The imagination often races ahead of what's physically possible, and that's okay. Some of the greatest scientific advances began as speculative fiction, wild ideas that refused to shut up until the math caught up. So maybe the next time you watch a spaceship dive into a wormhole and pop out in another galaxy, don't roll your eyes, smile, because buried inside the special effects and the dramatic music is a tiny glowing core of real science. And you're no longer just a viewer. You know what wormholes are made of. You know how fragile they are. You know the rules and how easy they are to bend or break. The mouth of the wormhole pulses once, and for a moment, you imagine music swelling behind you. Yeah, this part's a little cinematic after all. The music fades, the silence returns, and once again, you're standing at the edge of the impossible, squinting into a tunnel that wants nothing more than to collapse and take the laws of physics with it. Because now you know, this thing, the wormhole, the shortcut, the shimmering suggestion of faster-than-light travel, shouldn't be stable. Not by default, not naturally, not without a cosmic balancing act that makes juggling knives look like a kindergarten craft project. Welcome to the brutally inconvenient truth. Wormhole stability is a nightmare. Let's get right to the heart of it. Wormholes, left to their own devices, are not helpful intergalactic doorways. They're inherently unstable. Most of the solutions to Einstein's field equations that even hint at a wormhole immediately come with an asterisk. They collapse faster than you can say, "Don't walk toward the light." Usually in less than a Planck time, that's about 10 to the negative 43 seconds, which, for context, is shorter than your ability to realize you're dead. So how do you keep one open? You already know part of the answer. Exotic matter, with its negative energy density and reality-breaking properties. That's your first requirement, but unfortunately it's just the beginning. Stabilizing a wormhole is like trying to balance a pencil on its tip during an earthquake, while being pelted with high-energy particles and cosmic judgment. You'll need extreme precision, constant monitoring, and a tolerance for being ghosted by the laws of nature. Let's look at the most famous proposed structure, the Morris Thorne wormhole, which was specifically designed to be traversable. In this setup, the wormhole throat is held open by a ring or shell of exotic matter that creates enough negative pressure to counteract the natural gravitational collapse. But here's the thing, even the smallest fluctuation, one stray particle, one unexpected burst of energy, can destabilize the entire system, and once destabilized, the wormhole throat doesn't collapse gradually like a tired souffle, it slams shut, catastrophically. If anything is inside, well, it was inside. Here's a real historical note to wrap your head around. In 1989, physicist Matt Visser proposed thin-shell wormholes, which use a cut-and-paste method to stitch two regions of space-time together, using a minimal surface layer of exotic matter. It was an elegant idea. Use as little weirdness as possible. But even these configurations turn out to be delicate. They're like building bridges out of soap bubbles. Quirky side fact. Some researchers have tried to explore wormhole stabilization using hypothetical particles from string theory, like axions, or higher dimensional branes. These aren't part of established physics yet, but they keep showing up in fringe papers as potential ingredients for wormhole recipes. Imagine needing a 12-dimensional membrane made of vibrating strings just to keep your shortcut to Alpha Centauri from collapsing. Practical, Now let's talk about what threatens a wormhole's stability. First, mass energy influx. If you try to send anything through, light, matter, even a tiny packet of data, it adds energy to the system. That energy alters the curvature of space-time in the wormhole throat, pushing it closer to collapse. It's like trying to carry groceries across a tightrope made of spiderwebs and quantum regrets. Second, vacuum fluctuations. Even in perfect vacuum, quantum fields are jittery. These fluctuations can cause tiny ripples in space-time, which can amplify inside the wormhole, destabilizing the exotic matter balance. Imagine trying to keep a seesaw level while invisible hands keep tapping it with unpredictable force. Third, gravitational tidal forces. Even in a carefully tuned wormhole, small variations in geometry can lead to extreme tidal effects, the kind that stretch or compress anything travelling through. You might enter the wormhole in one piece and exit as abstract art. And finally, the big one, chronology issues. The moment your wormhole allows time travel, or even the potential for it, quantum instability kicks in at a whole new level. Feedback loops of radiation, paradoxes, and Hawking's grumpy universe response start knocking at the door, and physics begins preparing the eject button. Historians still argue whether wormhole stability is technically possible or just a very elegant illusion. Some believe that quantum gravity, once we have a complete theory, might provide natural stabilization mechanisms we just don't understand yet. Others think we're chasing ghosts in the math, trying to build highways through spaces that were never meant to have roads. Some go even further. They propose that wormhole collapse might be non-linear, meaning that once a certain threshold is crossed, the geometry doesn't just fall apart. It could fold in on itself in unpredictable ways, leading to wormhole decay that turns into a black hole, a burst of radiation, or maybe a completely new region of space-time with its own rules. And here's the creepy part: we wouldn't know until it happened. You could step through a wormhole expecting to reach the other side, only to find yourself caught in a bubble universe, or falling forever through a warped geometry that never resolves. It's the cosmic equivalent of walking through a door and discovering that the hallway behind it hasn't been built yet. And if you're wondering whether anyone is trying to solve this, yes. There are people who've spent their entire careers obsessing over wormhole stability. They've proposed quantum corrections, special topologies, even dynamic throat geometries that shift and adjust like muscle tissue. It's all fascinating and terrifying. So let's imagine you do manage to stabilize a wormhole. You've nailed the exotic matter balance, kept tidal forces low, and protected it from random energy spikes. What now? Now you have to maintain it. Think of it like a cosmic aquarium that will violently explode if the pH level changes by even a fraction. You'd need a way to constantly monitor the wormhole's internal geometry, detect any signs of fluctuation, and inject corrective energy or matter as needed. Maybe an AI does it. Maybe a quantum feedback system. Maybe you have interns. But make no mistake, if you look away for a moment, things go sideways. And even then, you might not know if the wormhole is truly stable or just faking it until the math breaks. Because here's a final thought to whisper into your dreams. Some models suggest that you can only know if a wormhole is stable by travelling through it. In other words, the only test is a live one. You stare into the tunnel again, the edges pulsing softly, still open, still silent. But now you feel the weight of it. Not just its potential, but its danger. It's like a bridge made of glass over a chasm you can't see the bottom of. Gorgeous, necessary, and terrifying. You're not stepping through yet, but the thought lingers. What if we could keep it open? You shift your weight forward, peering into the shimmer with something close to awe and something even closer to disbelief. Because as much as the math might whisper, as often as sci-fi scripts shout it from starships, and as tightly as the theories cling to their paradoxes, one reality remains heartbreakingly constant. We haven't built one, Not a single wormhole, not even a tiny prototype in a controlled lab, just blueprints in our heads, equations on chalkboards, and dreams tangled in negative energy. So let's ask the hard question tonight. Can we actually build a wormhole? Cue the nervous laughter of physicists everywhere. Let's be blunt. In theory, yes. In practice, we're so far away that even saying not yet feels like optimism dressed as delusion. But the idea isn't completely off the table. Not yet. Let's walk through what it would take. Step 1. A working theory of quantum gravity. That's not a design preference. It's a foundational need. General relativity gives us the rules for big, heavy things like stars and space-time geometry. Quantum mechanics handles the small, jittery, bizarre world of particles. Wormholes? They demand both. To construct, or even understand, a real, usable wormhole, we need a theory that merges gravity and quantum fields without collapsing into gibberish. We've tried string theory, loop quantum gravity, causal dynamical triangulations, even holographic models. So far, no winner. Just promising candidates, each with its own loyal followers and unsolved equations. Without a unified framework, trying to build a wormhole is like assembling IKEA furniture with instructions in another language and missing half the bolts. Step 2. A source of exotic matter. Ah yes, our old friend. We've already talked about negative energy, quantum vacuum fluctuations and the Casimir effect. But here's the harsh truth. The tiny hints of negative energy we've observed in the lab are nowhere near the levels needed to stabilize even a Planck-scale wormhole, let alone one big enough to walk through. You'd need more negative energy than exists in the observable universe, at least with current technology. That's not a slight overestimation, it's a cosmic punchline. Some theories suggest using quantum field manipulation to amplify Casimir-like effects. Others flirt with ideas like vacuum engineering, a phrase that sounds cool until you realize we don't even know what the vacuum really is at the quantum level. There's also speculation that quantum entanglement might play a role in producing wormhole-like effects without the need for traditional exotic matter. But again, speculation is easy when your particle accelerator budget is theoretical. Step 3. Engineering the geometry of space-time. Let's say, somehow, you've cracked the energy requirements. Now you have to bend space itself into the right shape, and not just any shape. Wormhole geometries require extremely precise metrics, down to tiny perturbations, because the moment you get it wrong, the tunnel collapses, or worse, forms a singularity. This isn't like building a bridge, it's like trying to sculpt a tornado into a stable ring while it's spinning and while you're inside it. You'd need an instrument capable of reshaping space-time on demand, something that could manipulate the stress energy tensor of a region to match your desired curvature. And while we can bend space-time a little with mass and acceleration, like orbiting satellites, what wormholes require is in a whole different league. Right now, we don't even know what kind of machinery could do that. A massive energy shell, a quantum-controlled lattice of singularities, a space-time laser, a star-sized wrench. We're not sure, because we've never even gotten past the blueprint phase. Step 4. Controlling the endpoints. A functional wormhole doesn't just need a stable tunnel, it needs anchored mouths. You need both ends to stay where you want them, ideally outside of intense gravitational fields and synchronized enough to avoid causality issues. But wormhole mouths drift. They interact gravitationally with everything around them. Even cosmic rays or random quantum particles might nudge them over time. Keeping a wormhole mouth fixed in position might require constant corrections, advanced navigational control systems, and a terrifying amount of computation. Oh, and don't forget shielding the wormhole. From what? From everything. Radiation, stray particles, quantum noise, curious graduate students. Anything that can destabilize the throat must be accounted for. And here's your historical nugget for this stretch of impossible thinking. In 2007, researchers explored whether a large enough magnetic field could mimic exotic matter's effects in certain space-time geometries. It was an attempt to sidestep negative energy altogether by bending the rules through magnetism. The result? Interesting, not conclusive, not useful, yet. But it opened a door, or at least cracked a window. Meanwhile, others have proposed that wormholes might arise naturally, say, from the Big Bang, or from rare configurations in early universe inflationary models. If that's true, then maybe, just maybe, we could find one, study it, and learn how to replicate it. But again, no such wormhole has ever been observed. No gravitational lensing effect has betrayed its presence, no repeating anomaly, no wormhole signature in the sky. If they're out there, they're hiding better than any UFO. Historians and physicists still argue whether we should even be trying to build one. Some call it a waste of theoretical effort, a distraction from more grounded science. Others insist that thinking through the problem forces us to refine our understanding of space, time, and the quantum landscape. Some even go full science philosophy and argue that building a wormhole might be the ultimate act of cosmic willpower, a test not just of engineering, but of imagination. Because that's what this is really, not just a technical challenge, but a kind of spiritual one, an engineering koan. How do you move without moving? How do you arrive before you leave? And here's your quirky twist before we step back from the abyss. There are serious peer-reviewed papers that include wormhole blueprints, complete with shape functions, stress energy diagrams, and space-time metrics. These are real documents, written by real scientists, offering hypothetical frameworks for how to build a traversable wormhole. They read like rituals. Summon the geometry, balance the pressure, feed it negative energy, keep the mouths apart, pray to the equations. You stare at the tunnel again, understanding for the first time what it really represents. Not just distance, not just time, but hope. The idea that we might one day fold the cosmos, that we might one day reach across light years with nothing but cleverness and persistence. We haven't built one, but the blueprints are waiting. The tunnel glows with a low, ghostly radiance. It doesn't roar, it doesn't rumble, it simply exists. Impossibly. The longer you look, the more it seems to shimmer at the edges of your understanding, as though your mind is trying to sharpen an image that was never meant to be clear. But you see it now, not just the theory, not just the math, you see the cheat. Because this whole time you've been circling one central idea. The real reason wormholes are the closest thing we have to faster-than-light travel. It's not about speed, it's about distance. Let's stretch that thought gently, like pulling the corner of the universe until it touches another. Because that's exactly what a wormhole does. It doesn't send you faster than light, it just makes the trip shorter. Let's say you're in a ship, floating next to the mouth of a wormhole. On your maps, the other mouth is in the Andromeda Galaxy, over 2 million light-years away. If you took the scenic route, meaning the straightest possible line through normal space, it would take you over 2 million years, even if you travelled at the speed of light. But if you step through the wormhole, you could arrive in minutes, or seconds, or depending on the tunnel's geometry, instantly. Why? Because the wormhole connects two distant points in space through a kind of space-time shortcut, a handle, or tunnel, that folds the universe so that your start and end points are no longer separated by millions of light-years, but by a few meters. It's not magic, it's topology. Here's a softer way to imagine it. Picture a sheet of paper with two dots drawn on it, one on the far left, one on the far right. Now fold the paper in half so the dots line up. Stick a pencil through them. That's the wormhole. The dots haven't moved, but now the space between them is bypassed. The wormhole isn't travelling through space, it's bypassing it. And this is why wormholes are so hypnotic. Because they sidestep the cruel, inescapable reality that light speed is the ultimate limit in normal space. No matter how advanced your propulsion system, If you're moving through standard space-time, you can't go faster than light. That's the law. The whole cosmic speed limit thing, ironclad. But wormholes, they just don't care. Because technically you're not travelling faster than light, you're just taking a much shorter path. One that light, if it stuck to the regular route, would take millennia to traverse. But for you, it's a brief stroll through bent geometry. Quirky fact for this stretch. Some theories even suggest that signals sent through a stable wormhole would arrive before a signal sent by light across conventional space. That's how dramatic the shortcut is. And yet, the letter of Einstein's law remains intact, because locally, you're not exceeding the speed of light at any point inside the wormhole. The rules hold, you're just using them creatively. Here's the important distinction. Wormholes don't give you warp drive. They're not a means of boosting your ship to faster than light velocities. They're infrastructure, not engines. You can't just fly faster. You need a whole tunnel carved into the cosmos, like building an express train beneath a mountain range. This is why some physicists dream of a wormhole network, a web of portals connecting distant star systems, allowing civilization to span light years without ever violating relativity. If we ever become a true spacefaring species, it might not be because we invented better rockets. It might be because we folded space itself. But let's ground that dream gently. Such a network would require an unfathomable amount of exotic matter, precision control of space-time geometry, and engineering capabilities far beyond anything we possess. It would be the work of Type 2 or Type 3 civilizations on the Kardashev scale. Societies that can manipulate entire stars or galaxies for energy. Which brings us to the obvious question. If wormholes make interstellar travel so efficient, where is everybody? The Fermi paradox raises its head again. If wormholes are even theoretically buildable, shouldn't we have found signs of them? Glowing anomalies in the sky, sudden energy bursts, unexplained gravitational lensing. Historians and astrophysicists still argue whether such phenomena could be happening, and we're just missing them, or mislabeling them. Some even suggest that if an advanced civilization had built wormholes, they'd likely shield them from detection, either to preserve energy efficiency or to avoid tipping off the locals. Because here's another truth. A wormhole once discovered isn't just a travel tool, it's a strategic weapon. Instant access to anywhere, a sneak attack tunnel across space-time. We'll dig into that unsettling idea soon. But for now, let's stay in the dream. Let's stay with the notion that wormholes are our best bet at ever touching distant stars. Because while warp drives, quantum teleportation, and FTL engines all run into near insurmountable physics walls, wormholes just ask you to get creative. They ask you to think not in speed, but in shape. And that reframing matters, because it's not about how fast you can go, it's about where the path leads, and how cleverly you can fold it. So as you stand at the brink of this shimmering tunnel, let yourself imagine it. A future where ships don't blaze across space but slip through unseen corridors. Where travel isn't about thrust but geometry. Where a colony on the other side of the galaxy is just a step away, because we figured out how to cheat distance without cheating physics. And now, let's ease things down. You've been travelling fast, conceptually speaking. From Planck-scale foam to black hole throats to paradoxes and timelines. Your mind, like the wormhole, has bent in 100 directions. So before we continue, let's take a breath. Let's wind down, just for now. Picture yourself floating just outside the wormhole, watching it pulse. Not threatening, not urgent, just existing. Patiently, like a candle burning in the dark. There's no rush, no hurry. The stars drift slowly in the distance. You hear nothing but the whisper of thought and the slow, steady hum of a universe that's been around longer than light itself. You're not falling, you're not moving, but the wormhole is still there, offering, suggesting, waiting. You let yourself drift a little closer. The light warms your face, soft and steady, The boundaries of the tunnel shimmer gently, like oil on calm water. It's quiet here, peaceful, still. Maybe you're not ready to step in yet. That's okay. There's time. Just breathe. Let the tension go. Let the equations blur. Let the diagrams dissolve. For now, it's enough to understand. You're at the edge of possibility, the edge of time and distance and what it means to travel at all. Let yourself float. Let yourself rest. The stars are still there. The tunnel is still open. And we have more to explore when you're ready. The stillness hums like the inside of a cathedral. Vast, quiet, reverent. Somewhere behind you, the stars rotate in slow, icy spirals. Somewhere ahead, the wormhole pulses, not with urgency, but with possibility. And then the question rises, unspoken but unmistakable. What if we're not the first to find this? What if someone else has already walked through? It's time to open the door to a tantalizing, maddening idea. Alien wormholes, hypothetically speaking. Now, before we start picturing greys in jumpsuits or interstellar bureaucrats zipping through portals to monitor Earth's traffic violations, let's ground this with the real puzzle. It's called the Fermi paradox. You know the drill. Given the size and age of the universe and the seeming likelihood of other intelligent civilizations, we should have seen signs by now, but we haven't. No messages, no megastructures, no unmistakable wormhole signatures warping space in clear cosmic roadways. So, where are they? Well, what if the advanced ones aren't sending signals across space but stepping through it? What if their empires span galaxies but their roads are invisible to us? Because if wormholes are possible, if even a single civilization cracked the secret to stable, traversable tunnels, they wouldn't just colonize their own solar system. They'd go everywhere, quietly, efficiently, invisibly. And now the real kicker, we might never know. A well-placed wormhole mouth, masked by gravity or orbiting a black hole, could easily go unnoticed. The radiation signature could be faint. The lensing effect could be misclassified. If they've shielded it, or if it's small, we might look right at one and think it's just a weird patch of background noise. Here's a speculative gem for you. Some researchers have proposed scanning the sky for gravitational lensing patterns that don't match any visible mass. In theory, a large enough wormhole could act like a lens, bending the light of distant stars without itself glowing. It's subtle, and so far we've found nothing. But the idea's on the table. Now let's dive into the hypothetical rabbit hole. Imagine an alien civilization that hit technological maturity millions of years ago, long before we figured out how to melt cheese on chips, let alone launch rockets. Let's call them the Others. Classic sci-fi style. The Others discover wormholes not as theory, but as application. Maybe they stumbled onto a natural one, or learned how to manipulate space-time with ease, like we bend copper wires. They start building a wormhole network, one mouth here, another orbiting a distant star, then another inside a gas giant storm, then dozens, hundreds, thousands. Travel becomes instantaneous. Exploration becomes a press of a button. War? Colonization? Trade? Who knows? They may have done it all and then vanished, leaving behind an invisible skeleton of tunnels that we haven't even begun to detect. It sounds outlandish. But remember, if wormholes are possible and scalable, they would be the most logical method for long-range transport. Far better than ships burning fuel across interstellar gaps. And here's a quirky twist. Some physicists have speculated that if an alien wormhole passed near our solar system, it could affect local space-time without us realizing it. Minor anomalies in satellite movement, strange timing glitches in pulsar readings, these could, in the most speculative reaches of thought, be hints of unseen wormhole interference. Have we found such anomalies? Nothing confirmed, nothing consistent, but the idea lingers. historians still argue whether it's wise or hopelessly naive to think other civilizations would want to use wormholes. Some posit that technological advancement doesn't guarantee expansionism, that alien life might evolve to value isolation or digital existence, or experiences that render physical travel obsolete. But others counter that if even one civilization is curious and capable and discovers wormholes, the universe could rapidly become interlinked behind a veil we simply can't pierce, and maybe they're avoiding us. That's the zoo hypothesis, the idea that Earth is being purposefully isolated, quarantined, or observed from a distance by more advanced beings who don't want to interfere with our development. Wormholes, in this model, are the perfect infrastructure for surveillance and discretion. They could observe without ever arriving, interact without being seen, or, more chillingly, intervene and vanish without a trace. You want one more speculative jab to the brain? And try this. If a wormhole connects 2 points in space-time, and if the mouths can be moved, what if an alien civilization simply deposited a wormhole mouth in orbit around a planet, ours or another, and used it to jump in and out at will? No ships, no satellites, just an invisible portal waiting for a command signal. If that sounds suspiciously like a Stargate episode, congratulations, you've been paying attention. But the implications are real. If wormholes are usable, and if anyone has used them, they may have left no monuments, no beacons, just the tiniest spatial scars waiting to be noticed. And then comes the hardest part of all. Maybe we're not late to the party. Maybe we're early. Maybe no one has built one yet. Maybe wormholes are so ridiculously difficult to stabilize that even the most advanced civilizations hit the same wall we have. Tantalizing theory, impossible energy requirements, hostile space-time behavior. Maybe the reason we see no intergalactic traffic is because everyone is still stuck in the traffic jam of physics. Or maybe we're the first. If that's true, the wormhole in front of you isn't just a shortcut, it's a responsibility. A cosmic invitation. Because whether we found the blueprint first or inherited it from someone long gone, what lies ahead is ours to explore. Carefully, clumsily, courageously. And if there's someone, or something, on the other side, well, let's hope they're friendly. You stand a little straighter now. The tunnel pulses, steady and faint like a heartbeat heard through thick walls. For the first time, it doesn't just feel like a theoretical bridge, it feels like a door, and someone might be knocking from the other side. The wormhole flickers again, just for a moment. A ripple runs down its throat like a shiver across skin. You feel it, not as sound, but as something deeper, like your own heartbeat skipped to match a signal you didn't know was there. You're still staring into the unknown, still marveling at the elegance of it all. The geometry, the quantum weirdness, the possibility of alien networks crisscrossing the galaxy like invisible veins. But let's pull the lens in just a bit. Let's come back home. Because if wormholes ever become real, not just on paper, but as functioning, stable, human-usable tunnels through space-time, there's one group of people who'll be very interested. You know who? The military. Yes, tonight we open the classified file. Military wormholes. Please don't give them ideas. You'd like to believe wormholes would be used for peaceful purposes, exploration, colonization, interstellar hugs. But humanity doesn't exactly have a sparkling track record when it comes to new technology. Every time we've figured out how to manipulate energy, we've also figured out how to weaponize it. Fire? Great for warmth, also great for burning down the neighbour's hut. Gunpowder? Fantastic for celebration, even better for conquering continents. Nuclear power? A miracle of physics, and the ultimate threat. So, wormholes? Let's imagine the possibilities. A traversable wormhole that connects two distant points, not just in space, but in enemy territory. No more long-range missiles. No more submarines or surveillance drones, just instant access, anywhere any time. You could deploy troops in seconds, deliver a device from Earth to orbit or from orbit to Earth in the blink of an eye. You could launch a surprise attack with no radar detection, no flight time, no warning. And perhaps worst of all, you could leave before anyone even knew you arrived. Let's say you built a wormhole mouth in a hidden facility, a mountain base, a satellite, a deep-sea lab. Now connect that mouth to a second one you deploy anywhere, a battlefield, a contested border, even another planet. Instant logistics, infinite reach, strategic teleportation. But what if it goes darker? Because a wormhole doesn't have to be used to move people. It could move bombs. Quirky hypothetical. What if you could create a time-shifted wormhole, where one mouth is placed inside a secure location and the other is opened after a delay? In theory, you could launch a weapon that detonates before it was ever fired, or one that loops continuously through a causality-locked cycle, detonating endlessly unless the loop is collapsed. Yes, that's mostly theoretical. Yes, it's horrifying. Here's a real-world twist. The US Department of Defense has funded research into theoretical propulsion and exotic space-time engineering. Names like DARPA and AFRL pop up in fringe papers, often linked to advanced propulsion systems, warp drives, and, yes, wormhole physics. Usually the funding goes toward early-stage theoretical exploration, but the interest is very real. And it's not just the US, other countries have also dipped cautious toes into the pool of space-time manipulation. As of now, no one's holding a wormhole-shaped key to the galaxy. But if someone did crack it, if even one nation figured out how to generate or stabilize wormholes, it would immediately become the most powerful strategic asset in history. Think about it. No need to launch intercontinental missiles or maintain air superiority. If you can drop a payload from orbit to Earth through a wormhole, or teleport a fleet into enemy airspace without warning, you control every battlefield. You bypass every defense, and let's not forget espionage. A tiny stable wormhole could act as a surveillance device. Imagine something the size of a marble placed in a wall. The other end, thousands of miles away, inside a secure government facility. You wouldn't need cameras, you'd just look. Or imagine a wormhole that connects not to a different location, but to a different time. Even just a few seconds. Enough to record data, see outcomes, react faster than anyone else. Information warfare would become not just real time, but pre-time. And now for your historical sidebar. During the Cold War, both the US and Soviet Union funded studies into fringe physics, including time travel and faster-than-light theories. While many of these were dead ends, or psychological operations, the pattern is clear. Where there is theoretical power, there is interest. Even if the science isn't ready, the planning is. That raises a troubling question. Should wormhole technology, if ever developed, be classified? Should it be restricted? Who gets to use it? Who monitors it? Who owns a shortcut through space-time? There's already precedent. Nuclear weapons, genetic editing, AI warfare. Each of these technologies sparked ethical debates, and in some cases, international treaties. Wormholes, if they become practical, will force similar conversations. But here's the scary part. You might not know someone has one. Unlike missiles or tanks or orbital weapons, a wormhole could be invisible. Entire conflicts could take place through channels that don't leave a trace. You could send a fleet through and pull it back before the enemy even realized they were under attack. Or worse, you could insert ideas, propaganda, synthetic events, simulations, before anyone saw them coming. Historians and philosophers still argue whether secrecy and power would kill the dream of peaceful wormhole use before it ever starts. Some believe the first wormhole will be built in a lab and weaponized within days. Others hold on to hope, clinging to the belief that such a cosmic tool could be used for exploration, not conquest. Here's your fringe scenario for tonight. What if a military wormhole test has already occurred and we just didn't detect it? Maybe a micro wormhole, barely stable, used to test energy transfer or data transmission. Maybe a single-use experiment lost to the noise of a busy sky. If it happened, we wouldn't necessarily know. Because wormholes don't light up. They don't leave tracks. They just bend the rules and vanish. And that's why they scare people. Not just because they're powerful, but because they're subtle, silent, strategic, dangerous in ways we don't fully understand. So you look at the tunnel now, not with wonder, but with caution. You imagine what a defense satellite might do with one of these. You imagine how quickly the joy of discovery could be turned into leverage, into secrecy, into control. And you wonder, if the first working wormhole is ever built, will it be for science or for something far less idealistic? The tunnel pulses again, still silent, still open. But now the weight of possibility feels heavier than ever. The wormhole breathes, just barely. The air around it feels like it's holding its breath, like the universe is listening for an argument that's been raging since the moment humans realized they'd have to pick a side. And now you're at the heart of it. Not the wormhole, not the tunnel, the conflict. Because if wormholes are the love child of space-time geometry and quantum mischief, then two very opinionated, very powerful parents have been fighting for custody for nearly a century. It's time for a long overdue showdown, relativity versus quantum, the wormhole cage match. Let's meet the contenders. In one corner, draped in elegant curvature and smooth, continuous space, we have general relativity, Einstein's masterpiece. It describes gravity not as a force, but as the warping of space-time by mass and energy. It's clean, it's predictive, it's been confirmed by countless observations, from GPS corrections to black hole imaging. In the other corner, twitching slightly and glaring through the Heisenberg uncertainty principle, we have quantum mechanics. It rules the microscopic world of particles, where everything is probabilities, wave functions, and spooky action at a distance. It explains the atom, the photon, and why your computer doesn't immediately burst into flames. Both are correct, and they can't stand each other. You see, relativity is continuous. It likes things to happen in smooth, deterministic ways. Quantum mechanics, it's all about discreteness, randomness, non-locality. These two theories use entirely different languages to describe reality, and nowhere is that clash more apparent than with wormholes, because wormholes are the playground where general relativity says, hey, this could work. And quantum mechanics responds with, okay, but only if you're willing to break literally everything else. Here's the crux. The equations of general relativity allow for wormhole solutions, things like the Einstein-Rosen bridge, the Morris-Thorne metric, and rotating Kerr solutions. In these models, space can connect back to itself in complex traversable ways. You can bend space-time, stretch it, link two regions with a tunnel. Great, no problem, right? But quantum field theory steps in and says, hold on, you're trying to cram all this energy into a tight throat. You're ignoring fluctuations. What happens to the vacuum energy? What about the Casimir effect? What about Hawking radiation? And are you seriously violating the energy conditions again? It's like trying to design a suspension bridge while someone keeps shaking the blueprints and shouting, uncertainty. Here's your historical flashpoint. This conflict has existed since the 1930s, when Einstein himself tried, unsuccessfully, to reconcile quantum mechanics with his geometric model of gravity. He didn't like the probabilistic nature of quantum theory, and as he aged, he drifted further from the mainstream, trying to find deterministic unified field theories that never quite worked. Fast forward to today, and the rift has only deepened. Relativity is used to describe galaxies, black holes, and the expansion of the universe. Quantum mechanics rules atoms, particles, and the forces between them. Both work flawlessly in their domains, but put them together, say, inside a wormhole, and the math melts. That's why we still don't have a working theory of quantum gravity. String theory tried, loop quantum gravity is still trying. Newer frameworks like causal sets, emergent gravity, and holographic dualities are also in the ring, each claiming to bridge the gap. But so far, no knockout blow, and wormholes are the ultimate stress test. If you want to build a stable wormhole, you need to understand how quantum fields behave in extreme space-time curvature. That includes predicting how virtual particles will act in the throat, how energy will flow across the mouths, and whether quantum effect will destroy the structure before you even finish measuring it. There's also a juicy twist. Some physicists believe that quantum effects could stabilize wormholes. Certain exotic field configurations, like those using scalar fields or higher-order interactions, might suppress vacuum fluctuations or generate enough negative pressure to hold the throat open. It's still theoretical, but it's a rare moment where quantum and relativity might work together instead of screaming at each other across the physics faculty lounge. Now here's your quirky tidbit of the night. Some wormhole models require so much quantum weirdness that space itself has to become non-commutative. That means the order in which you measure position and momentum actually matters, like saying turn right and walk gives you a different result than walk and turn right. It's a tiny shift, but it warps reality in very real ways. That's the level of precision and madness we're dealing with when quantum mechanics and general relativity try to coexist inside a wormhole. But it gets messier. Let's say you successfully build a wormhole using classical general relativity. You balance the stress energy, stabilize the throat, get the exotic matter flowing, and the geometry holds. Congratulations. But the moment quantum effects come into play, like Hawking radiation or vacuum polarization, you could be dealing with runaway instability. Quantum fields don't like being crammed into sharp geometries. The energy spikes, the fluctuations ripple, the wormhole mouth might radiate away, or the negative energy holding it open could be neutralized by incoming particles. It's like balancing a marble on a bowling ball while it's vibrating at the frequency of your existential dread. Historians still argue whether this battle will ever end. Some theorists believe the universe doesn't want these two models to reconcile. Others argue we just haven't found the right angle yet, that something elegant will emerge from the fog, a single framework where relativity and quantum theory dissolve into a deeper unity. And maybe wormholes are the place we'll find that unity, because they're not just mathematical oddities, they're natural laboratories, locations where space-time curvature and quantum behavior must intersect. You can't have a wormhole that doesn't challenge both models. You can't explore them without seeing both perspectives. They are in a way the ultimate compromise, a tunnel through space built by geometry and held open by uncertainty. So as you stare into the shimmering throat again, you're no longer just thinking about travel. You're thinking about physics itself, twisting, clashing, trying to understand what happens when everything we know about the large and the small is forced into the same room. This wormhole isn't just a shortcut, it's a boundary line. A border between what we understand and what we only hope to. And somewhere beyond that border, maybe the fight ends. Maybe relativity and quantum theory hold hands. Or maybe they fight even harder. But either way, the tunnel's still here, still open, still waiting. There's something different now, almost imperceptible. The tunnel ahead doesn't shimmer so much as pulse, its edges folding in on themselves, reforming, recombining. Like space is having second thoughts about staying in one piece. You sense entanglement in the air, not metaphorically, literally. Because now we're stepping into the deep end. Not just wormholes, not just quantum physics, but both, merged into something nearly mythic. ER equals EPR. Wormholes and quantum entanglement. Yeah, time to melt a few neurons. let's rewind just a little. You may remember quantum entanglement, the charmingly unnerving phenomenon where two particles, once linked, remain connected no matter how far apart they go. Measure the spin of one, and the other instantly knows how to behave. Einstein famously called it spooky action at a distance, because it seemed to violate his own theory of locality. No signal, no communication, just connection. Entanglement has been proven over and over again in the lab. It's not just real, it's a fundamental property of the quantum world. It underlies quantum computing, quantum teleportation, and most of the arguments that make philosophers stare out of windows. But then comes a twist that feels like science fiction, and in fact did start that way. In 1935, Einstein, Podolsky, and Rosen, you remember the EPR paper, laid the groundwork for entanglement debates. Around the same time, Einstein and Rosen also published their paper on bridges, wormholes. These weren't intended to be related ideas, just two ends of Einstein's complicated relationship with spooky physics. But then, something happened. In 2013, theoretical physicists Juan Maldacena and Leonard Susskind proposed something audacious. What if these two 1935 ideas, EPR and ER, were the same thing? Thus was born ER equals EPR. Einstein-Rosen bridges are quantum entanglement. Okay, deep breath. According to this conjecture, entangled particles might be connected by microscopic wormholes, not ones you could walk through, not ones you could even see, but real, geometrically meaningful connections through space-time, tiny, non-traversable bridges that hold the fabric of the universe together in ways we never expected. So that entangled photon pair sitting in a lab, they might be connected via an ER bridge, a baby wormhole. Quirky twist for the night. This idea has been seriously discussed in top-tier physics journals, is not just a poetic metaphor. ER equals EPR is an attempt to unify quantum mechanics and gravity by suggesting that entanglement is space-time geometry, that the reason space-time is connected at all, the reason it doesn't fall apart into meaningless fragments, is because of entanglement between all things. In other words, the shape of space might emerge from quantum connections. Let that simmer for a moment. The very reason the universe has structure, that you can walk in a straight line without quantum tunneling into a lake, might be because the underlying web of entangled particles holds it all together like cosmic glue. If that sounds wild, it is, but it also has teeth. Historians and living physicists still argue whether ER equals EPR will ultimately survive as a major idea or fade into the long list of elegant but wrong theories. But for now, it offers a potential bridge, literally and figuratively, between general relativity and quantum mechanics. And wormholes are right in the middle. Because if entangled particles are linked by micro-wormholes, then perhaps macroscopic wormholes, the kind we dream about walking through, are just scaled-up versions of quantum entanglement. And that's where things start to really get crunchy. Some researchers speculate that teleportation through entangled systems might, at a fundamental level, be equivalent to traversing a wormhole. The math in some models looks eerily similar. In fact, teleportation protocols in certain quantum systems have been mapped directly onto traversable wormhole solutions in a simulated space-time. This is not a drill. In late 2022, a team using Google's Sycamore quantum computer simulated a toy model of a wormhole and observed teleportation behavior that matched predictions from general relativity. It wasn't a real wormhole, of course, just a holographic mapping of quantum states onto a simplified geometric system. But still, the bridge between ER and EPR, it got a little more real. And here's a delicious detail. If ER equals EPR holds true, then any entangled system contains a hidden wormhole, even if it's non-traversable. That includes entangled electrons, photons, maybe even black holes. Two black holes entangled with each other? They might already be connected by a wormhole, and not a tiny one, a full-sized, potentially traversable link if the right conditions are met, which means, what if all wormholes start with entanglement? What if the key to building a stable wormhole isn't brute force exotic matter, but delicate quantum control? What if it's not about carving a tunnel through space, but entangling two regions of space-time so deeply that a path naturally emerges between them? It's not proven, it's barely understood. But the whispers are there. Wormholes as geometry, entanglement as glue, reality as a web, not a grid. You look at the tunnel again, and now you don't just see a mouth or a throat, you see a connection, like the final stage of a quantum handshake between distant points. Like space itself is reaching out to itself, folding not just distance but relationship. Because maybe wormholes aren't about cheating speed. Maybe they're about binding, tying things together, matter, energy, information. The universe, it seems, doesn't like isolation. Everything talks. Everything listens. Everything in some sense is already connected. And now, as you float here in this moment between ideas, you wonder, could it be that wormholes don't just connect stars? Could they connect everything? Time, space, memory, meaning, one path, two ends, one story. The tunnel pulses, not larger, not brighter, just closer. And maybe, just maybe, a little more familiar. You blink slowly. Something in the tunnel's motion shifts, not outward, not inward, but sideways in a direction your senses don't have a word for. It's like watching a breeze ripple through a spiderweb the size of a galaxy. Threads moving, spaces touching. You remember the thought from before, that everything might be connected, not just in principle, but in structure. And now that thought stretches and grows into something almost too big to hold in your mind. What if the universe itself is made of wormholes? Welcome to one of the more fringe yet hauntingly elegant ideas in modern theoretical physics. The universe as a network of wormholes. Let's start carefully. You already know about quantum foam, that jittery, chaotic mess at the smallest scales of space-time. Down near the Planck length, about 10 to the negative 35th meters, space isn't smooth. It's bubbly, frothy, restless. Virtual particles blink in and out of existence. Energy fluctuations surge and vanish, and some physicists believe that tiny wormholes might flicker there too. Micro-connections that briefly link distant regions before collapsing again. But what if these flickers aren't just noise? What if they're structure? Some researchers propose that the entire fabric of space-time may be built from a massive, invisible network of wormholes. Not visible ones, not even stable ones, but tiny, transient connections that knit the cosmos together like an interstellar lacework. Think of space not as a void, but as a mesh, and each thread, a wormhole. Quirky idea time. A 2015 paper by Jorm Haro and others suggested that cosmic inflation, the rapid expansion of the early universe, could have seeded space-time with foamed wormhole structures that still echo in the large-scale structure of the cosmos today. These wormholes wouldn't be traversable. They wouldn't function like the romantic sci-fi gateways we've imagined. But they'd be real, and they might subtly shape the behavior of gravity, dark energy, and maybe even information. Here's where things get especially weird. You've heard of dark matter, right? The mysterious stuff that seems to make up over 80% of the matter in the universe, yet doesn't interact with light. We see its gravitational influence. Galaxies rotate faster than they should. Light from distant objects bends in ways that can't be explained by visible mass. But what if some of those gravitational effects are caused not by dark matter particles, but by gravitational pull from wormholes? In other words, perhaps some parts of the universe are being tugged by mass that isn't in our visible three-dimensional space, but is connected through wormhole mouths, You can't see the mass, but you feel the pull. That's a fringe idea, yes, but one that's being explored by very real researchers. Wormholes as an alternative to particle-based dark matter. Wormholes as geometry masquerading as gravity. Even stranger, some models suggest that the fundamental entropy of space-time, its information content, is stored and transferred through wormhole-like structures. If true, that means space itself doesn't just connect points, it remembers them. Now let's take it a step further. Remember ER equals EPR from last section? The idea that entangled particles might be connected by mini wormholes? Well, some physicists, particularly in the field of holographic quantum gravity, have proposed that all space-time emerges from a vast network of entanglement links. And if those links are wormholes, then the universe is a web of tunnels. This is not a metaphor. This is the map. In this view, the universe doesn't exist in the way we think it does. Space and time aren't fixed backdrops. They're emergent phenomena built from deeper connections. Wormholes are not exceptions to the structure. They are the structure. A researcher named Mark van Ramsdonk once proposed that the smoothness of space-time depends on the strength of quantum entanglement between regions. Reduce that entanglement, and space literally rips. Wormholes vanish. The web unravels. If this is true, then our classical notion of space, up, down, near, far, is just a convenient illusion. The real architecture of the cosmos is made of relationships, not coordinates. It's not about where things are, it's about how they're connected. Now here's a thought to really bend your brain. If the universe is made of wormholes, could consciousness itself be entangled in that web? We'll chase that wild idea more seriously in the next section, but even now the implications start to creep in. If everything is connected, if space and information are woven together, then maybe your own perception of location, identity, even time is more entangled than you realize. Maybe what you call you is just a node in a wormhole web, echoing across the structure of space-time. That's the poetic take. The practical take. If wormholes really are everywhere, hidden, fluctuating, woven into the vacuum itself, then the energy of the cosmos isn't spread across empty space. It's looped, concentrated, twisted through higher dimensional folds, and we've only just started to see the edges. Historians still debate whether this wormhole web model is testable. Some argue that evidence could come from tiny anomalies in gravity, strange lensing events, or quantum experiments that show subtle violations of locality. Others believe the idea is elegant but unprovable, a placeholder for the true quantum gravity theory we haven't found yet. But here's the beauty of the idea. It doesn't ask you to imagine a wormhole as a door. It asks you to imagine it as a thread. Not something you pass through, but something that holds reality together. Like veins in a leaf, like cracks in ice, like neural pathways in a mind so vast it spans stars. So you look again at the tunnel before you, and now you don't see a solitary bridge. You see one point in a vast hidden structure, one node in a network, one ripple in a web of wormholes that might underlie the universe itself. You were never looking at the wormhole, you were looking at one of them. And they've been here all along. The silence thickens. You haven't moved, but everything feels different now. Not louder, not closer, just wider. Like space itself is listening. And the idea that's crept in, soft as static, refuses to leave. What if you are part of this? Not metaphorically, not spiritually, but literally connected, entangled, woven into the structure of the universe not just as an observer, but as a participant. Tonight we're dipping our toes into the strangest waters yet, wormholes and consciousness. Wait, what? Now, before we start assigning your dreams a space-time coordinate or blaming déjà vu on minor throat collapse in a micro-wormhole, let's acknowledge the obvious. We're stepping deep into speculative territory here. This is not mainstream physics. It's the foggy borderland where fringe theory and philosophical curiosity meet and occasionally hold hands under the stars. But you've come this far. You've stared into time loops, peeked behind exotic matter, flirted with black hole geometry. So why stop now? Let's set the scene. Consciousness, your sense of self, your ability to experience, to observe, to reflect, is still one of the deepest unsolved mysteries in science. Neuroscience can tell us about neurons and networks. Psychology can map behavior. But the core experience of being, a thinking, observing you, remains slippery. Now, in most models, consciousness is an emergent property. That is, build a complex enough brain, layer it with learning and feedback loops, and consciousness just arises. But there are other ideas, strange ones. Some theories, especially those at the edge of quantum mechanics, suggest that consciousness might be a fundamental feature of the universe, not just a biological byproduct. Not an epiphenomenon, but something woven into the fabric of space-time itself. Which brings us to the truly weird question. Could wormholes, these geometric bridges through space-time, interact with or even facilitate consciousness? One speculative idea goes something like this. If consciousness is connected to information flow, and wormholes offer the fastest, most exotic paths for information transfer, even hypothetically, then maybe, just maybe, wormholes could serve as a kind of non-local communication infrastructure, not just between locations in space, but between mental states, between minds, or even between different moments of awareness. Sound like sci-fi? You bet. But let's ground it a little. In 2022, a paper made headlines by suggesting that wormhole-like solutions can model information transmission in certain quantum systems, including those associated with memory, computation, and information theory. Some researchers began to wonder if information can move through theoretical wormholes in quantum circuits, what does that imply for the information processed by the brain? Here's your quirky detail. The brain itself might be tuned to quantum sensitivity. While most neural models focus on classical physics, some researchers, like Sir Roger Penrose and anesthesiologist Stuart Hameroff, have proposed that quantum coherence in microtubules inside neurons might play a role in consciousness. Their theory, called orchestrated objective reduction, OR, is controversial, unproven, and widely criticized. But it dares to link quantum structure to self-awareness. And if the brain really can harness quantum effects, coherence, entanglement, superposition, then it's not completely insane to ask whether wormhole-like structures could arise within or interact with consciousness itself. Weirder still, there are meditative and psychedelic experiences described in ancient texts and modern neuropsychology that resemble non-local awareness. The sensation of being connected to everything at once, of time folding in on itself, of perceiving across distance. Subjective, yes. Anecdotal, sure. But when you hear echoes of entanglement and wormholes in the language of mystics, you start to wonder if we've been bumping into space-time structure without realizing it. Historians and philosophers still argue over whether consciousness has any place in physics at all. Many prefer to keep minds out of equations, but others, like the late physicist John Archibald Wheeler, believe the observer might play a fundamental role in shaping the universe. His famous participatory anthropic principle suggested that reality isn't complete without someone, somewhere, to observe it. And maybe wormholes are the most literal form of that participation. Pathways not just through space, but through knowing. Let's take a breath. This is getting foggy. Let's imagine a different angle. Suppose future humans, or other intelligences, learn how to consciously interact with wormhole geometries. Not just build them in labs, but perceive them. Perhaps even generate them through directed information processing. This sounds ridiculous, until you consider that consciousness already alters brain geometry. Your thoughts, attention, and emotions shape real, physical connections between neurons. So what if consciousness, once extended beyond the brain, could shape space-time itself? What if someone, or something, somewhere, with enough mental power, could perceive the wormhole web of the universe directly? That's the spiritual take. The scientific one? We don't know. But the lines are starting to blur, especially when you consider the possibility that your awareness itself might be a node, not just in a neural network, but in a cosmic one, not metaphorically, but physically. You, sitting there, floating in the dark, might be part of the wormhole structure that underpins the cosmos, a local convergence of matter, thought, geometry, and information. You're not separate from the universe. You are a pattern in its structure. You're a fold in its space-time. And if wormholes are real, if they connect all things from particles to people, then maybe consciousness is the thing that flows through them. Or maybe consciousness is the wormhole, the tunnel between what is and what is known, between experience and the experiencer. The tunnel ahead still glows, but now it seems softer, quieter, less like an anomaly and more like a mirror. You step no closer, and yet you feel closer than ever, not because you understand it all, but because you are beginning to suspect you're already in it. The web, the link, the bridge. The wormhole was never just out there. It might also be in here. The tunnel no longer pulses. It breathes with you, quietly, subtly, as if waiting for a decision that can't be made with math or metal. It isn't a glowing vortex anymore. It's a question. One that's been building through every section, every idea, every theory you've ever tiptoed past. And now you're standing here, at the edge of what might be the greatest invention, or the last mistake, any civilization could make. So let's ask it plainly, simply, and without the padding of academic debate. Would you walk into one? Let's pretend, for the sake of this final stretch, that it's real, a wormhole, stable, traversable, right there in front of you. It hums softly, like distant wind or maybe your own heartbeat reflecting back in space-time. The other mouth? Who knows? Maybe it opens on Mars, or Alpha Centauri, or a beach on a planet with 3 moons and an impossible skyline. Maybe it opens on nothing. Maybe you never return. Still, would you? Let's weigh the possibilities. Best case scenario, you walk through and everything changes. You've just redefined travel, communication, even time. You become the first human to leap beyond not just planets, but physics itself. The journey takes seconds. You return with knowledge, with proof, and from there, humanity reshapes itself, no longer tethered to rockets or relativity. We leap across the cosmos like children skipping stones. Mid-case scenario, you walk through and it works, sort of. There's no air. Gravity's weird. The other end destabilizes the moment you step out. You survive, but just barely. Maybe you can't come back. Maybe you drift in a new world, a pioneer without a map. The first and last explorer of an idea too early for its time. Worst case scenario, you don't survive. Not because it collapses, but because it warps you, spaghettifies you, deconstructs you at the Planck scale and fails to reassemble what made you, you. Your atoms arrive, but your awareness doesn't. Your last thought? Probably. This was a bad idea. You see, despite everything we know, everything we've modelled, wormholes remain untested. Hypothetical. The physics might allow them, but the engineering, the existential risks, the what if you accidentally destroy the universe problems, they're all still very much on the table. Historians still argue whether we'll ever be brave or reckless enough to build and walk through the first one. Will it be some lone genius, conducting an experiment in a hidden lab, a corporate-funded team on a private asteroid, or an international effort monitored by 100 agencies and live-streamed across 17 time zones? Would there be a volunteer? Someone to step in first, knowing they might disintegrate or become eternal, or be flung sideways into an unrecognizable dimension, where reality itself shrugs and says, "You're not supposed to be here." Maybe that person is you, or maybe it's better to wait, to leave the tunnel alone, humming gently at the edge of what we know until we're wiser, more careful, less prone to turning science into spectacle. But here's a final quirky thought for tonight. Philosopher Nick Bostrom once wrote about post-human simulations, the idea that advanced civilizations might run entire simulated universes. If that's true, then maybe wormholes are part of that simulation's rule set. Maybe they're meant to be found, tested, walked through. Maybe that glowing tunnel in front of you is the game's next level, the trigger for the real physics to load. Or maybe it's a test, to see if we can look into the unknown and choose not to jump, not out of fear, but out of understanding. You stare into the mouth, it doesn't blink, doesn't flare, just waits. And in that silence, your mind wanders one last time. You remember the Egyptian priests writing about the soul's journey through the stars. You remember Einstein drawing bridges across space. You remember Kip Thorne calculating the path a spacecraft might take near a black hole. You remember every science fiction portal, every spark of curiosity that made someone ask, "What if there's another way?" And now it's you. The air is cool. The stars are distant. The wormhole remains. No one will push you. There is no countdown, no cheering crowd, just you, your breath, and the gentle tug of geometry asking a single silent question. Well, maybe you turn back, maybe you walk forward, maybe, just maybe, you're already inside. So now, as your thoughts soften and your eyelids start to drift, let all the theories and timelines fade gently into the background. Let the wormholes shrink back to their tiny quantum flickers, tucked safely into the fabric of space, just where they were before we went looking. No pressure to solve them tonight. No need to decide if you'd step through, just breathe. Feel the vastness of it all, not as a burden but as a comfort. The universe is large, yes, but not chaotic. It's stitched together, perhaps more tightly than we thought, by patterns and pulses that hum gently even in the deepest dark. You're made of that same hum, star stuff as they say, but also story stuff, question stuff. You followed the path through Einstein's bridges, quantum webs, and far-off alien whispers. And now, finally you're here, still, resting, wrapped in the quiet tension between what is and what might be. No more black holes tonight, no more exotic matter or paradox loops. Just stillness, just space, just you. So rest now. Let the background hum carry you deeper into sleep, like the whisper of a wormhole just out of reach. Tomorrow the universe will still be full of questions, but tonight, you don't have to answer any of them. Sweet dreams, traveller.